Hey guys, today we're looking at section 5.5, which is going to talk about mean value theorem and Rolle's theorem. So for example 1, it says consider the graph over here on the interval from -4 to 0. Draw the secant line through the endpoints of the interval, then sketch any parallel tangent lines. So my secant line that's going to go through my endpoints from -4 to 0, it's just going to be a horizontal line straight across right there. So let's actually have it go through the points. There we go. And so any parallel tangent lines also have to be horizontal tangent lines. And so we're going to have a parallel tangent line up here where we've got that horizontal tangent line. So how can we prove that this tangent line that we drew is parallel to the secant line? So my goal is to show that the slope of the tangent line equals the slope of the secant line. So I'm going to say the slope of the tangent is equal to the slope of the secant. So how can we find the slope of a tangent line? So tangent line is our instantaneous rate of change. So for my tangent line, I'm going to take the derivative, f prime of x, to find the slope for that tangent line right there. So f prime of x is going to equal, well, I'm going to bring that 2 down, so I'm going to have -2 times x plus 2 to the first power. Then the derivative of the inside, because technically this is a chain rule. The derivative of x plus 2 is just 1. And the derivative of that plus 4, well, that's just 0. So I could rewrite this as -2x minus 4. So there is my derivative. How can we find the slope of a secant line? Well, that's my average rate of change. So for that one, I'm going to do f of 0 minus f of -4 over 0 minus a -4. So it ends up being plus 4. Well, f of 0 is 0, minus f of -4, also 0, over 4. Well, that just gives me 0. So what we're going to do here is we're going to put our steps 2 and 3 together to achieve this goal. So I'm going to say that -2x minus 4 has to equal that 0 right there. That's our goal here. So I can add 4 to both sides. So -2x equals 4, and divide by -2, so x is equal to -2. And if you look at x is equal to -2 is where that tangent line is. So does our answer match our graph? Yes. Yes, it does. So we have a theorem that goes with this, and it is Rolle's theorem. So Rolle's theorem says, let f be continuous on our closed interval and differentiable on the open interval if my endpoints have the same y value. So if f of a is equal to f of b, then there's at least one number in c in that a-b interval such that f prime receives equal to 0. So if our two endpoints are the same, that means the secant line between the two endpoints is 0, and in between those 2 points, there's got to be a tangent line that also has a slope of 0. So what if our slope is not 0? So Rolle's theorem only deals with 0. Let's see what happens when our slope is not 0. So this time we have the graph 5 minus 4 over x, and we are looking on our interval from 1 to 4. So from this point right here to this point right here. So let's draw our secant line. Our secant line is going to go through those 2 points. Ooh, I did not draw that very well. There we go. Goes through our 2 points. So is there a tangent line that's parallel? So it kind of looks like maybe at 3 right here we would have a tangent line that's parallel, possibly. So let's check that out and see if that matches. So once again, our goal is to show that our slope of the tangent line equals the slope of our secant line. Ooh, I cannot spell today, secant line. So how can we find the slope of our tangent line? So our tangent line is going to be our derivative. So let's find our derivative. I'm going to rewrite this as 5 minus 4x to the -1 power. So the derivative of 5 goes away. The negative 1 is going to come down and multiply by the negative 4, so it's going to be a positive 4x, and now to the negative 2 power. So 4 over x squared is how I'm going to write that one. Then to find the slope for our secant line, that's our average rate of change. So I'm going to do f of 4 minus f of 1 over 4 minus 1. So f of 4 is 4, minus f of 1 is 1, over 4 minus 1, so 3 over 3, which is just equal to 1. So once again, I'm going to set those two parts equal to each other and see what happens. So 4 over x squared has to equal that 1. Oh, wrong color. Our secant line was in red, so 1. So I'm going to multiply both sides by x squared, so 4 is equal to x squared, and take the square root of both, so x is equal to plus or minus 2, and that matches right here at our point 2, 3 is where we had that tangent line sketched in. So does this match our graph? Yes. So when our slope is not 0, instead of Rolle's theorem, we use mean value theorem. So mean value theorem says if f is continuous on the closed interval a to b and differentiable on the open interval a to b, then there exists a number c such that f prime of c is equal to our average rate of change, f of b minus f of a over b minus a. So what are the necessary conditions for both theorems? So both of these, it has to be continuous on our closed interval and differentiable on our open interval. So if I were to sketch a couple of examples, one could be this kind of cubic function, one could be a quadratic, anything that's continuous and differentiable. Some non-examples would be the absolute value, where I've got that sharp turn right there. It's not differentiable. Or let's say a piecewise function that's got an open point here, but then it connects up here. That one's not continuous. Or like even our rational parent function, also not continuous. So it has to be continuous and it has to be differentiable. And it's continuous on the closed interval with the brackets and differentiable on the open interval with the parentheses. So it doesn't have to be differentiable at the endpoints, but it does have to be continuous the whole way through. So we must show that down here where it says what does it mean, we must show that it's continuous and differentiable. Ooh, big text. Let's go smaller. Must show that it is continuous and differentiable. If you guys haven't guessed by now, I am not great at spelling. There's a reason I am a math teacher and not an English teacher. Okay, so let's look at example 3. So we're going to consider our function f of x is equal to a negative x squared minus x plus 6 on our interval negative 2 to 2. So we need to verify that the mean value theorem can be applied. So we need to show that it's continuous and show that it is differentiable, which this is a normal quadratic. So since it's a quadratic, we know that it's continuous and differentiable. So what I'm going to say here is that f of x is a quadratic. So f of x is continuous on my closed interval negative 2 to 2 and differentiable on my open interval negative 2 to 2. So that should always be your first statement when you are doing a mean value theorem. We have to say that it is continuous on our closed interval and differentiable on our open interval. So we're going to use the mean value theorem to find all values of c on the intervals such that f prime of c is equal to f of b minus f of a over b minus a. So I'm going to go ahead and take my derivative for this side right here. So my derivative would be a negative 2x minus 1 based off of this function right here. And then for the other side, I need to figure out what f of 2 minus f of negative 2 over 2 minus the negative 2 is. So I know the bottom's 4. Let's see what f of 2 is. And let's see what f of negative 2 is. So a negative 2 squared minus 2 plus 6. Negative 4 minus 2 plus 6, which is going to give me 0. And then a negative 2 squared. And this one's going to be plus 2 plus 6. So that's going to be a negative 4 plus 2 plus 6. So that's going to give me 4. So I'm looking at 0 minus 4. So this whole thing right here is going to give me a negative 4 over 4, which is equal to a negative 1. So I'm going to come back over here, and I'm going to say that this blue right here needs to equal a negative 1. So I can add 1 to both sides, so a negative 2x is equal to 0, and divide both sides by a negative 2, so x equals 0 is our value for C that our mean value theorem guarantees for us. So just real quick, I'm going to show you how you would write out that explanation dealing with our mean value theorem. So, like I said, you need to start with the f of x is continuous and differentiable, so I'm going to say f of x is continuous on my closed interval negative 2 to 2 and differentiable on my open interval negative 2 to 2. So the mean value theorem can be applied and guarantees a value C on my interval, open interval from negative 2 to 2, because we can't use negative 2 or 2, those are our endpoints, such that, and then it guarantees this right here. It guarantees this highlighted part right here. So I'm going to go ahead and write that out such that f prime of C is equal to f of B minus f of A all over B minus A, and our value of C is 0. So that's kind of how you would write that out. So a lot of times it'll just ask if the mean value theorem can be applied. So in that case, you won't necessarily say what that value of C is, but if it does ask for that value, you do need to include that value and include this work up here that's in red and blue. So part C says find the equation of the tangent line through C. Well, I know that my slope right there is negative 1, so I know I'm going to have negative 1. I know my x1 is going to be 0. I just need to find what y1 is. So what happens when I plug 0 into this function up here? So f of 0 is going to give me a negative 0 squared minus 0 plus 6, which gives me 6. So I can say that y1 is 6. So y minus 6 is equal to 1 times x minus 0, or y minus 6 is equal to x, or y is equal to x plus 6. Any of those are correct answers. Oh, my bad. It's negative 1. Negative 1, negative 1, that would be a negative, and that would be a negative. Negative 1. All right, so that is example 3. Let's look at example 4. So it says let f be a twice differentiable function such that f of 2 is equal to 5 and f of 5 is equal to 2. Let g be the function given by g of x is equal to f of x. So explain why there must be a value c for 2 to 5 such that g prime of c is equal to 1. So the first thing we need to show is that g is continuous and differentiable. And we know that because g is just a composition of our function f, and it says that f is twice differentiable. So if it's differentiable, that means it has to be continuous. So I'm going to go ahead and type that part out. G of x is continuous on our interval, and we're going from 2 to 5, so I'm going to say closed interval 2 to 5, and differentiable, I can't spell, on my open interval 2 to 5 because f of x is twice differentiable. I really can't spell. Differentiable Thus, the mean value theorem can be applied. Wow, that was rough. And I still spelled that one wrong. Okay, so since it's continuous and differentiable, the mean value theorem can be applied. So we can go through and say that g prime of c has to equal 1 if our f of 5 minus f of 2 over 5 minus 2 equals that 1. So that's what we need to check. So f of 5 is 2 minus f of 2 is 5 over 5 minus 2. So 2 minus 5 is a negative 3. 5 minus 2 5 minus 2 is 3. So if we're looking here, I have a negative 3 over 3. Oh, but we're not actually looking at f of x. We're looking at g of x. Wow, I'm sorry, guys. We're looking at g of x. So I need to show that g of 5 minus g of 2 is equal to 1. So if I'm looking for g of 5, that's going to be our f of 5. So f of 5, well, f of 5 is 2, so we're looking at f of 2, which gets me back to 5. So I'm going to have 5 minus, and this is all over our 5 minus 2, which is 3. And now let's find g of 2. So f of 2 is equal to f of 5, which just gets me back to 2. So 5 minus 2 is 3 over 3, which gives me 1. So that does check out. Make sure you're paying attention to the problem, like I clearly wasn't. So that does check out. And so we can say that the mean value theorem can be applied. And guarantees a value c on my interval 2 to 5 that's open, such that g prime of c equals this whole fraction right here, which equals that 1. And I will write in the fraction because I can't really type in fractions here. So g of 5 minus g of 2 over 5 minus 2, and it equals our 1. So that would be our part A right there. Explain why that has to happen is because of our mean value theorem. So now part B says show that g prime of 2 is equal to g prime of 5, and use this result to explain why there must be a value k such that g double prime of k is equal to 0. So once again, we're starting with our mean value theorem, and it did tell us that f is twice differentiable, so that does mean that g prime is also going to be continuous and differentiable. So I'm actually just going to copy and paste this because I don't want to deal with typing it out again, because you guys saw I clearly cannot spell. So I'm just going to change this to g prime of x is continuous and differentiable because f is twice differentiable, thus the mean value theorem can be applied. And so now let's check it out and see if it works out for us. So g of x is equal to f of x. So g prime of x, we're going to have to use a chain rule. So g prime of x is going to be f prime of x times f prime of x. So once again, we're looking on 2 to 5, and we're trying to show that it has to be 0. So I'm going to look for g prime of 5 minus g prime of 2 all over 5 minus 2. So g prime of 5, I'm going to do that over here. So it's going to equal f prime of 5 times f prime of 5. Well, up here from our original, f of 5 is 2, so f prime of 2 times f prime of 5. And so we need to figure out what those are, which we don't know, but it just says that we need to show that these two are the same. So let's see what g prime of 2 is going to give me. So I'm going to also do that up here. G prime of 2 is going to be f prime of 2 times f prime of 2. Well, f of 2 up here is 5. So I'm looking at f prime of 5 times f prime of 2, which these two are in fact the same thing. So we have shown that they're the same thing. And here, I'll go ahead and move this all down. Ooh, that did not work for me. There we go. I'll move all this down right here, so it's actually under the problem. So if they're the same thing, that means that this right here is just going to be 0. So I'd have 0 over 3, which is just 0. But remember, we don't have to use mean value theorem. We can use our Rolle's theorem here, because we're specifically looking for where our slope is equal to 0. So instead of saying mean value theorem can be applied, I'm going to say Rolle's theorem can be applied. So thus Rolle's theorem can be applied. And if you remember back here from our definition for our Rolle's theorem, if f of a is equal to f of b, then there's at least one number such that f prime of c is equal to 0. So I can say that, oh, wrong slide. I can say that the Rolle's theorem can be applied, and since g prime of 2 equals g prime of 5, there must be a k in our open interval 2 to 5, such that, and we're talking about g prime, so it would be g double prime of k equals 0. So that's kind of how you can go through and walk through that and explain that using Rolle's theorem. So remember, Rolle's theorem is dealing when our slope is 0. Mean value theorem is dealing when it's not 0. That is it for this video. You do have a Go formative that goes with this, so please make sure that you get started on that. If you have any questions, you can always come to my tutoring times. You can ask me during class, or you can send me an email and I will answer you as quickly as I can. So you guys get started on this Go formative and have a good day.